Hi, this is part 4 of my series of presentations about the best methods to convert aldehydes into secondary alcohols. This video is about the use of organotin compounds as carbon nucleophiles. The use of stennanes in organic synthesis is no longer as popular as it was 40 years ago, mainly because these highly lipophilic compounds are toxic and often difficult to separate from the product of a synthesis. Today, many alternatives to the use of stennanes exist, even in radical chemistry, where stennanes show a particularly valuable and unique reactivity. Anyway, despite this drawback, there can be instances where the use of stennanes as carbon nucleophiles is still a reasonable option. Organotin compounds can be prepared from tin tetrachloride and organoaluminum or magnesium reagents. Tetraalkyl stennanes react with tin tetrachloride at room temperature to yield mixtures of trialkyl tin chlorides and alkyl tin trichlorides, and at higher temperatures dialkyl tin dichlorides. Organotin chlorides can be reduced with sodium to tin hydrides, which are valuable reducing agents for organic halides or carbon-centered radicals. Tin hydrides can also be added to olefins or alkynes. A further procedure for the preparation of methyl tin chlorides is the direct synthesis from metallic tin and methyl chloride at high temperature, just like the process for preparing methyl chlorosilanes. Industrial applications of stennanes include their use as stabilizers of polyvinyl chloride and as biocides, for instance for the protection of wood and for the prevention of the attachment of aquatic organisms to the hull of ships. Unfortunately, some organotin compounds are highly persistent in the environment and quite toxic, and legislative restrictions beginning in the late 1980s led to intensive research for alternatives. Like silanes, most organotin compounds are unreactive and require some catalyst to undergo reaction with weak electrophiles. Instead, stennanes can also be transmetallated into more reactive organometallics, for instance into organolithium, palladium, titanium, or rhodium compounds. Simple tetraalkyl stennanes do not usually react with aldehydes. When treating tetramethyl tin with para-nitrobenzaldehyde and titanium tetrachloride, no secondary alcohol but a low yield of a benzylic chloride resulted. The same reaction with tetrabutyl tin instead of tetramethyl tin did not yield any alkylated product, but only a small amount of the reduced aldehyde. Thus, tin-bound alkyl groups require some special structural features to enable their transfer as carbon nucleophiles to aldehydes, or transmetallation. This is an example of stoichiometric transmetallation of a stennane to an organotitanium reagent. Interestingly, the transmetallation with titanium tetrachloride could be performed in the presence of the aldehyde. The starting organotin compound was prepared by addition of tributyl tin hydride to methyl acrylate. This is an intramolecular version of the same titanium tetrachloride mediated alkylation of an aldehyde with an alkyl stennane. Both the preparation of the intermediate aldehyde and the oxidation of the secondary titanium alkylate were conducted in the same reaction vessel, without isolation of any intermediate. Like we saw with alkyl silanes, alpha-haloalkyl stennanes can also be sufficiently reactive carbon nucleophiles for the alkylation of aldehydes. In this example, fluoride catalysis was sufficient to bring about the transfer of a trifluoromethyl group from tin to 4-dimethylamino-benzaldehyde. Stennanes transfer allyl groups to aldehydes much more effectively than alkyl groups. The main reason for this is the beta effect, which refers to the strong stabilization of carbocations in beta position to a silicon or tin atom, which causes an increase of electron density at the gamma carbon of the allyl group. This effect can also be visualized by resonance structures, in which electrons from the metal carbon sigma bond are pushed into the allyl group, or the positive charge is delocalized into the metal by formation of a metallus cyclopropane. A comparison of the rate of the iodine-mediated dealkylation of various stennanes clearly shows how powerful the beta effect is for tin. Tin-bound cyclopropyl methyl groups, for instance, which often behave like allyl groups because of the increased p character of cyclopropane carbon atoms, react 79 times faster with iodine than methyl groups. Allyl groups react 10 orders of magnitude faster than methyl groups, and phenyl groups react faster than cyclopropyl methyl groups. Thus, allyl and aryl stananes are much more reactive than alkyl stananes, and much better suited as carbon nucleophiles. In this example, an allylic tributyl stanane was first transmetallated diastereoselectively with tin tetrachloride into a new allyl trichlorostanane. This intermediate reacted with benzaldehyde already at -78 degrees Celsius without the need of any additional catalyst. It was found that methanol increases the allylation rate of aldehydes and some ketones by allyl stananes. For instance, tetraallyl tin reacted with isobutyraldehyde and methanol at 30 degrees Celsius within 24 hours to the expected secondary alcohol. In dichloromethane, almost no reaction was observed. The authors proposed that this rate acceleration was caused by hydrogen bonding between the carbonyl group and methanol. Allyl stananes can also be generated in situ in the presence of aldehydes, for example by treatment of allyl iodides with tin dichloride. Here, the required allyl iodide was prepared in situ from an allyl chloride and sodium iodide. The rate of nucleophilic arylations of aldehydes by aryl tin compounds can be enhanced by transition metal complexes. In the example on this slide, the arylation was catalyzed by 2% of a rhodium complex, but still required 60 degrees Celsius to proceed at an acceptable rate. This is an example of an alkynylation of cyclohexane carbaldehyde by an alkynyl tin trichloride. Organotin trichlorides are more reactive than tetraorganotin derivatives because a covalent bond is formed by chloride displacement between the carbonyl oxygen atom and tin, and the alkylation can proceed intramolecularly without the need of any additional catalysts. This reactivity is analogous to that of trichlorosilicon enolates. The main advantages of organotin reagents as carbon nucleophiles are their ready availability and high stability. These reagents are also more chemoselective than polar organometallics. Often, however, their reactivity is too low, what narrows the scope of this chemistry and demands catalysis or high reaction temperatures. The main disadvantages are the toxicity of some organotin derivatives and the difficulty of their complete removal from the reaction product. For most industrial applications, this last issue is crucial and precludes the use of organotin reagents for the large-scale production of agrochemicals, drugs, vitamins, and other fine chemicals. A number of unexpected side reactions can occur during nucleophilic alkylations with organotin reagents. One of them is the Oppenauer oxidation of the intermediate secondary alcoholate by the starting aldehyde. In the example on this slide, all 4 tin-bound alkynyl groups added to the aldehyde, but the twofold excess of aldehyde caused a complete oxidation of the alcohol to the corresponding ketone. Despite their high chemoselectivity, stananes can also transfer alkyl groups to other electrophilic functional groups, such as ketones or imines. Also, electron-deficient olefins and alkynes may react with stananes, sometimes even faster than with aldehydes. Then, stananes can undergo protonolysis, but usually only under harsh reaction conditions. Tin-carbon bonds readily undergo homolytic cleavage, but can also yield carbon radicals in the presence of mild oxidants. Therefore, in particular in the presence of copper catalysts, stananes may undergo homocoupling. Finally, some allyl stananes can be isomerized thermally, what can also lead to unexpected byproducts. Here are some further recent examples, but as already mentioned, organotin chemistry is hardly applicable anymore to large-scale preparations, and therefore of low general interest. Research efforts should better be spent on finding better procedures for rendering polar organometallics more selective and safer to handle. In the next videos, the use of various enolates for the alkylation of aldehydes will be presented. See you then.